All right. Thank you, everyone, for coming. Before starting, let me introduce myself. My name is Jose, and I am a consultant, author, and instructor based in London. I'm the author of Microservice APIs, and I'm the founder of microapis.io. So MicroAPIs is the company that I use to offer my consulting and teaching services. And Microservice APIs is a book where I've tried to collect the experience that I've collected over the past years, helping organizations from all over the world, small and big organizations, in all matters related to APIs and microservices. Our recurrent topic in this space is API security, which is the reason for this webinar. I hope to help you raise awareness of API security issues and how to improve the security of your APIs when you're working with them, when you're implementing, designing, or architecting your systems. I'm available in different platforms, so if you want to connect with me, please do so in Twitter, GitHub, or LinkedIn. I also have a newsletter. I'm trying to get a constant cadence of getting publications once a week. And I'm also going to launch soon a specific section for API exercises. So if you are interested in that, please check it out. So the agenda for today, we're going to talk about API security, and it's a big topic, actually. There is a lot of ground to cover. I realized that while I was preparing it. So I won't be able to deep dive into any of these topics. I want to keep it down to an hour. And the way I want to approach this topic is I want to talk first about the OWASP top 10 list of API vulnerabilities. And I want to cover both the 2019 and the 2023 list. Then I'm going to talk about API authorization and authentication, and I'm going to do that through the lens of Open Authorization and OpenID Connect, which are the most commonly used protocols to handle these operations on APIs. I'm going to talk also about how our API design can compromise security in certain cases. So that won't be an extensive analysis, but what I want to give you is some heuristics so that when you're designing your APIs, you have some ideas in mind on how it can affect the security of your API. I'm going to talk about the components surrounding the API that can compromise security. So APIs are not standalone elements. They sit within a system. There is probably a database behind the API. There is a cache store sitting besides the API. The API runs on certain infrastructure. There is a network configuration and a load balancer in front of it. So all of these elements come together to help us operate and productionize the API. And security issues in any of these components can compromise the security of the API. So again, this won't be an extensive survey of all those elements, but at least bring up to your attention some of the main elements we need to have in mind when configuring and architecting our systems to ensure that our APIs are secure. And finally, I'm going to say a word about automating the process of API security testing. With that said, let's get started. So OWASP top 10 API vulnerabilities. What is this? So first of all, OWASP is an organization that does a lot of work in the space of software security. They do a lot of research, and they do a lot of work to raise awareness about the main issues that affect the security of our software. The acronym stands for Open Worldwide Application Security Project. That's a recent change. Before it used to be Open Web Application Security Project. And so the reason for the change is because they actually deal with security across the whole stack of software developments, including IoT devices and embedded software and whatnot. So they work across all areas of software development to investigate and raise awareness about security issues. And in 2019, they started a specific chapter dedicated to APIs. Reason being, APIs are becoming really popular, and they've become one of the main gateways into our systems, but also one of the main security holes. So there was this rush recently to expose APIs and to put APIs across our systems. But the thing is, building an API is a simple process, but building a resilient, reliable, and secure API is a completely different matter. It's just like software, right? Anyone can write software, but writing good software is difficult. So as a consequence of this rush to join the so-called API economy, we have a lot of applications out there running with a lot of issues. So OWASP has collected the main types of security vulnerabilities that affect APIs, and the 2023 list is here. So what do we have in 2023 for this list of vulnerabilities? We have broken object level authorization, broken authentication, broken object property level authorization, unrestricted resource consumption, broken function level authorization, server-side request forgery, security misconfiguration, lack of protection from automated threats, improper assets management, and unsafe consumption of APIs. Just one word also here, the 2023 list is still in release candidate status. We are discussing currently on GitHub whether this list is correct, whether we should make any changes to it. Something that has been highlighted is that there is probably a missing item, important one here, which is injection. So the 2019 list had injection, but that's not present here. And in my experience, actually, injection is still a very relevant topic in many types of APIs, especially those that are kind of data science, machine learning types of APIs, because often we have to write complex manual queries and we forget to parameterize those queries, right? But for many other reasons also, many other API consultants find this is a very relevant topic in 2023 still. So there might be changes to this list, but in any case, I'm going to cover 2019 also. So hopefully that covers everything. Let's get down into each of these categories. So broken object level authorization. What is this? This is the ability of a user to access a resource that doesn't belong to them. Most APIs have a concept of resource ownership. If you think, for example, about a blogging application, I can make a post, and as the author of the post, I'm the only one who should be able to make edits or changes to the post or to delete it. Broken object level authorization happens when another user can do that. And typically this happens because we fail to have user-based access controls in our endpoints, in this implementation of those endpoints. So most APIs are going to have some sort of middleware to validate access to the API via tokens. So a global component somewhere in our code that is going to check that every request coming to the server has a valid token. But that is the first degree of access we need to check. The second degree of access is to ensure that in every endpoint, the user has access to the operation they are requesting. So here is an example. We have publications from user 1 and user 2, and a malicious user here is able to launch a request to the API and get access to publications that don't belong to them. Get is perhaps not the best example here. Maybe it should be put or delete, because anyone should be able to read those resources, or maybe not. Depends on the API, but anyways, that's the idea. All we need to do is make sure in every endpoint, in every root view, every framework has different terminology. Make sure that we are making those checks. Every user, we need to validate whether they have access to the operation or the resource they are requesting. Next one is broken authentication. Authentication is the process of verifying a user identity. It's typically the login process. There are a lot of things that can go wrong here, from weak password policies to weak token signatures to lack of rate limiting for these endpoints. These are very sensitive endpoints. We need to be very strict on how we allow users to access these endpoints. We need to have strict rate limiting policies, because otherwise anyone can do a brute force attack and try to crack down a password for a specific user. It can also be weak token validation mechanism. Like I said, every API is going to have its own middleware to validate tokens. If we don't do this in a robust way, we open the door for users to bypass these access controls in our API. I'm going to talk more about token validation later, but here is an example. A user bypasses this authorization access control by sending a token without a signature and setting the signing algorithm property of the token to none. That means there's nothing to validate. So in some implementations, this can bypass our access controls and get access to the API. So we want to make sure that doesn't happen. One of the best ways to protect ourselves against this type of vulnerability is by outsourcing authentication to a third-party provider, something like Auth0, Okta, or Cognito if you work with AWS. So unless you are a very large organization like Microsoft, Google, Facebook, or Uber, or something similar, it's probably not worth the effort of your organization to implement its own authentication or user service and to handle all these security traps and all these complex processes yourself. It's very complicated. It's full of protocols that are difficult to understand and to implement. So it's usually best to delegate this to an external service. Now, next one is broken object property level authorization. So we talked about object level authorization before, and that is the ability to access a resource that doesn't belong to you, right? In this case, is the ability to access properties of an object that you shouldn't be able to access. And this can happen in two different ways. Is when we disclose properties to a user that they shouldn't be able to read, and when we allow them to overwrite properties that they shouldn't be able to change. This category in 2023 brings together two categories of 2019, what that used to be excessive data exposure and mass assignment. So excessive data exposure is when we expose too much data to our users. It comes in many different flavors. One of them, for example, has to do with the design of our API precisely. Imagine we have a ride-sharing application and a user books a ride, and they can get the details of the ride through a request to the API. And in the response payload, we include information about the driver, perhaps the name, we include information about the car, but there is a chance that we include too much information in this response. We may include the ID of the driver and the ID of the car, which is unnecessary in this case and may open the door for a malicious user to leverage this information and launch surface attacks on the API and try to get control of those resources. So this is something we really want to prevent. We want to make sure we are only exposing data that our users need. The next type of strategy here is the mass assignment attack. So this is when a user can overwrite a property in our system that they shouldn't be able to change. Most applications have a concept of server-side or read-only properties and a concept of writable properties. Mass assignment happens when a user can overwrite those read-only properties. So typically there is a created or updated timestamps for an object, the ID of an object, but also the status of a payment process, right? So if we have this kind of flow in our application to allow payments, then a user places an order for a service, and then they can make changes to this order. But if we have a status of how the order is going, then maybe they can figure out that they can change the status themselves and send a request to set the status to paid. Then they don't have to pay. To protect ourselves against this type of vulnerability, first have a robust and good design of the API. Make sure we are not exposing, in any case, properties that the user shouldn't see. So in the previous case, make sure those IDs are not here. In this case, make sure that the status property is not part of the schema when we send an update request to the API. That's the first stage. The second stage is make sure we have robust validation of these payloads. So if we have the schemas, we want to make sure that our validation process in the API is robust. And if the payload contains any invalid property, we reject the request. So the design doesn't include the status property in the payload. If a user sends that property, we reject the request. That's a secure way of protecting ourselves against this type of attack. And finally, have an explicit translation between layers of your software, explicit translation of data. So we have the API layer, we get data from the user in that layer, then we are going to move this data to the business layer, and we have an explicit data transfer process. The pattern is usually called data transfer object. Basically, the idea is we are explicitly mapping input from the user to a business object, and we explicitly grab those properties that we know we should be using and disregard the rest. But again, let's have this good design and robust validation in place before, because it can save a lot of trouble down the line. Next one is unrestricted resource consumption. This refers mostly to the lack of rate limiting in the API, but it is more than that. First of all, obviously, rate limiting is very important. If we don't do rate limiting, we open the door for any user to be able to launch a DDoS attack against our service, a denial of service attack, to bring our services down. There are different strategies to launch a DDoS attack. It can be by launching a lot of different requests per second. So like here, a malicious user may have a host of servers, and from every server, they are going to launch thousands or millions of requests against our API. But it can also be by analyzing our API, a user may discover that there are certain slow endpoints that may be computationally and memory expensive. So by launching just a few simultaneous requests against these endpoints, they may be compromising the performance of our servers. So what we want to do is, for those expensive endpoints, we want to have a stricter rate limiting policies to make sure we don't overload our servers at any single time. And then we want to rate limit using different strategies. We want to rate limit by IP, by user account, and perhaps by operation, region, depending on the business model, depending on our application requirements, anything that makes sense to limit the amount of usage that users can make of our API, that's a good strategy. And the other side of this story is that if we are using the cloud, often our services can scale without limits. And that can put us in a very difficult situation. If a user successfully launches millions of requests against our API and the services scale to the sky, then we may become bankrupt. The bill may be too high. So let's have also a limit on how much our services can scale and how much resources any request or any process can consume. If you're using containers, that's pretty easy. You can set constraints on the container of how much memory and CPU they can consume. But if you can put constraints on every thread, process, request, every node, every pod of your architecture, then do it. You will be in a better position to handle this kind of attacks. Right, next one is broken function level authorization. Most APIs have a concept of user groups, user functions, hierarchies. Most classical distinction is between normal users and admins, right? So what happens sometimes is admins may have access to the API through specific endpoints, like a subdomain or a specific URL path. An attacker may figure this out and try to access those endpoints. Now, this is not necessarily bad. The problem is if we fail to have function access checks in those endpoints, if we assume that everybody who's coming through these endpoints is because they have a valid reason to do it. We should never have those assumptions in our APIs and anywhere in our software, really. So what we need to make sure is in every endpoint, we are not only making sure that the user can have access to whatever they are requesting, but also that they belong to the right group to perform whatever operation that they're requesting to do. By default, it's better to reject any request if we can't prove the user association with the requested resources, or if we can't prove the user belonging to a certain function. It's better to reject the request and deal with this separately. Better be safe than sorry here. That's what we need to do. In every endpoint, especially in the sensitive ones, make sure that we are figuring out which group or function the user belongs to. All right, next one, server-side request forgery. This is a new category in the 2023 list of API vulnerabilities. What it means is the ability of a user to launch requests from our servers, maybe to a malicious site, perhaps to download some malicious code and hijack our servers, perhaps to launch a DDoS attack against all the services, but also includes the possibility of launching requests to our internal host, so our local host. And a user may want to do this to do a port scanning, for example. So if a user includes a URL, for example, localhost 5432, that's the Postgres default port, they may figure out that we have certain databases or certain services running inside the server. And by leveraging this information, they may find a way to break into our system. The way this happens is sometimes we need input from the user in the form of URLs. So if we have a user profile page and we want to allow them to set the profile photo, we may want to allow them to indicate a URL that pulls an image from a gravatar they have on a different site. Or maybe we have a webhook. They need to include the URL that we're going to call as part of this webhook flow. It's difficult to be fully protected against this type of attack. But what we can do is, whenever possible, let us whitelist certain domains. Maybe we can blacklist certain domains. We can use regexes to make sure only certain patterns are allowed. And we can also run the URL through a scanner to see if it is pointing to a malicious site. And also treat whatever is coming from the endpoint carefully. Let's sanitize the output. It's a difficult vulnerability to handle, but as many measures we can take in this line, the better we will be. Next one is security misconfiguration. This refers to any kind of configuration around the API. It can be configuration of our infrastructure, S3 buckets, database. In terms of the API, it includes things like enforcing TLS, course policies, making sure that every URL path only exposes the HTTP methods that it's supposed to expose. So if a certain URL path is only supposed to expose a GET method, let's make sure we don't expose any others. Important here also, make sure we don't leak stack trace in our error responses. This happens all too often, and it's brilliant for malicious users because then you gain a lot of information about the system. You may know which databases you're using, which programming languages you're using, And all of this information can facilitate the design of an attack strategy against our services. So make sure you are using safe configuration policies, and if you can, do continuous testing of this vulnerability in your system, and make sure you're continuously improving your position in this space. Next one is lack of protection from automated threats. This category is also new in 2023, and this is actually the most difficult to handle from an API point of view. What it means is that a user can leverage knowledge of your business model behind the API to cause harm to your business. Imagine you have an e-commerce site, something like Amazon or Shopify platform, and you have different sellers in your marketplace, and there is a product launch coming up. A malicious user can be monitoring the launch of the product, and as soon as it becomes available, they can buy the whole stock by using bots across different regions of the world, using different accounts. It's very difficult to prevent. If a user is using that kind of a strategy, using different servers, then they have different IPs, different accounts, then it's difficult to correlate actions between those different accounts. But there are some things we can do from an API point of view to limit this threat. The first thing we can do is, if we are expecting interactions from a browser-based client or something like that, then we can disable requests coming from a headless browser. That would be most likely a bot. We can also look for non-human patterns of interaction with the API. If a user is adding too many items to the cart too quickly, and then they proceed to check out in less than a second, that is likely not a human, it's likely to be a script. So we can ban those requests straight away. If all of those requests are coming from the same user, we should be strictly prohibiting those requests immediately. We can block the user. If they're coming from the same IP, we can do the same. But again, it's a difficult vulnerability to handle, and we need to collaborate here with business intelligence and with application security to make sure we have as many measures as possible in place to protect ourselves against this type of attack. How this can happen, we may have malicious users sending this kind of requests to our API. We're collecting traffic logs, but we are not doing anything with them. So the first thing we should be doing is collect those logs and put them somewhere that we are actively monitoring and doing some analytics on those logs, drawing insights and put them in a dashboard. Every time you want to be able to answer questions such as what is the user's journey through the API, whether we have errors, what are those errors, what are the most commonly used endpoints. And also we want to be able to detect those unusual or non-human patterns in the use of our API so that we can take immediate action against them. Next one is improper asset management. So in terms of APIs, an asset is anything that allows us to interact with API. It includes API versions, servers, API endpoints. And the idea here is that sometimes we are rolling out new versions of the API, or we are changing the endpoints or something, and we forget to deprecate or to remove the previous endpoints or the previous versions. Also, servers. If we have a development server, a staging server, those servers are usually not as protected as the production server. So they may represent a gateway into our system, less secure one, and attackers who find out about those servers may be able to use this opportunity to break into our system. So if we have development or staging servers, let's make sure they are not publicly exposed. And as far as possible, let's make sure that they have the same access controls that we have in production. Because even if they are not supposed to be publicly exposed, a simple error in network configuration may expose them publicly, and that would be a very bad thing. But also, let's have a very robust process for managing API versions and changes to the API. So if we roll out a new version of the API, let's make sure the previous API is carefully deprecated and eventually shut down. And we need to make sure that happens, because if the new version contains security improvements, then the previous version represents a dangerous security hole in our system. And also when it comes to endpoints, our APIs are going to evolve, they are going to change, we're going to have new endpoints, we're going to deprecate old ones. Let's make sure our API documentation is always up to date, because if we change the endpoints and we are supposed to be deprecating certain endpoints, and those are maybe not in the documentation, but we forget to delete them from the code, then a user who finds out about them may be able to find a way to break into our system. So the thing to do here is make sure documentation is always up to date and make sure we roll out versions in a robust way. An example here, we have API version number 1, API version number 2. Number 2 contains security improvements. Let's say, like the example we had before, we were not checking the token signature. If the signature is set to none, then we want to make sure version 1 is shut down as soon as possible. Otherwise, an attacker can break into version 1 and therefore into our system. Next one is unsafe consumption of APIs. This is also a new category in 2023. And it's an interesting one because it is actually true that when we are consuming third-party APIs, we usually don't worry too much about the security of those responses. We don't think that they may be including malicious code or unsafe responses of any kind. But that may not be the case. And not because the site is necessarily vulnerable or anything like that. It's because users can find ways to inject malicious code into those services and put our services at risk when we consume that code. For example, imagine we have user account details in a third-party service, and for some operation, we need to access their address details from that service. So a user might find a way to inject malicious SQL code as the address in that service. When we consume that code, if we run it straight away, just like that, against our database, it's going to have very bad consequences potentially. So what we want to do here is have a zero trust approach to data regardless of the origin. So zero trust approach, obviously, to user input, that's very well known, but also to data coming from third-party integrations and even from our system. So if a user is sending SQL injection code through the API to our system, and that code is parameterized and then safely stored in the database, it doesn't run because it's parameterized, it is treated as a string, we put it in the database. If we need to reuse this code later in some different context, the code may get executed as a SQL statement, and that would be a very bad thing. So let us not trust data that is coming even from our own system. Zero trust approach in all cases, that is the best way to handle these situations. And the final vulnerability I'm going to cover is injection, and that is from 2019. Let's see if it gets included in 2023. I think it's very relevant. I see it in many APIs. And basically, it is the ability of a user to inject malicious code into our system through the API. And not only a SQL code, it can be SQL, NoSQL, or even command injection. So if we have an endpoint that accepts input that is going to be part of a command for a batch process or something similar, that code may get executed and a user may be able to leverage that to hijack our server and launch a DDoS attack against all the services. So what we want to do here is, first of all, it comes down to the design first. These kind of attacks are going to come through strings usually. So whenever we have streams, if we can constrain input via enumerations or regular expressions or something similar, let's do that. If we can't, the next stage is to do some checks in our code, make sure the input makes sense for the use case. Finally, we want to parameterize our queries in the database. The easiest way to do that is using an ORM, but ORMs may not be usable in all cases. So if we have very complex queries, it's perhaps easier to write them manually, but let us make sure that those queries are always parameterized. That is the only way we can stop those injection commands from hijacking our services. So that's the OWASP top 10 list of vulnerabilities. This is an example of SQL injection. So a user may send a request to get a specific post from the API, from the blogging application, and instead of putting an ID, we are using here a SQL injection command. This may get run against the database, and then we may be losing our users table or something like that. So that was OWASP, top 10 API vulnerabilities. Hopefully that gives you an idea of the ways that your APIs may go wrong from a development point of view and some of the ways you can improve the security position of your APIs. Let's now talk about authentication versus authorization. So authentication is the process of verifying a user identity, and in many cases also the process of giving them an access token to our APIs. And authorization is the process of verifying that a user has access to our API. We usually handle authentication with OpenID Connect, and we usually handle authorization with Open Authorization. The reason is because they are very well established and robust standards. They require some understanding. So that's what I'm going to do here. Try to give you a basic idea of how they work. With a good understanding of how these protocols work, you may be able to have a very robust authentication and authorization access controls to your API. Open Authorization basically is a protocol for access delegation. It allows a user to grant access to an application to data they own in a different application. There are a few important concepts here. We have the resource owner, which is the user. The resource server is the server that contains the data. The client is the application that is requesting access to the data. And the authorization server is the service that issues the access token to allow the client to access that data on behalf of the user. So to grant these access tokens, Open Authorization has a concept of flows, and we have different flows for different use cases. This is super important. We need to make sure that we are using the right flow depending on our use case. Otherwise, we open the door for malicious users to game our system and get access tokens when they shouldn't. So the first of them is the authorization code flow. This is a classic flow. It is designed for applications that have content or the UI dynamically rendered in the system. So if you work with Django, that is using Django templates. With Flask would be Jinja templates with the ability to generate content in the server, to render it and then send it to the browser. It doesn't work for SPAs. SPAs use a different flow. So the idea here is the user, they get the UI, and then they make a request to the API. If the request doesn't have an access token, then we create a signed URL, redirecting them to the authorization server, and the URL contains some parameters. One of them is the service that we want the user to request access to, and that is going to be our API. So the user signs in with the authorization server. If that's successful, the authorization server issues an access code. And then they are redirected to our website. Then we can grab the URL and the code in the URL, and we can exchange the code for an access token. We give the token to the user, and then they can continue interacting with our website just as normal. All of this is hidden from the user. All they're going to see is I go to the website, I don't have credentials, I go to the login page, and then I'm redirected to the target page, the home page, or whatever page they were requesting. What we're doing behind the scenes is we are orchestrating the flow. We are creating the signing URL, we are grabbing the code, we are exchanging it for an access token, and we're validating the token on every successive request to the server. A slight modification of that flow is the PKCE Flow, so proof of key exchange flow. And this is an improvement on top of the authorization code flow, and it's actually now recommended to use PKCE Flow also with applications like Django with content dynamically rendered in the server because it is more secure. So the idea here is it was originally designed for SPAs, single page applications. So a user comes to the SPA has to access the API, but if there is no token, they can't do it, right? So they are redirected to the login page. And when the user logs in with the page, the client code, in this case, the SPA, creates a code verifier and a code challenge. And when they send the authorization request to the authorization server, they send the code challenge in the first request. If login is successful and the user is authorized, then the authorization server responds with an authorization code response. This is the response that includes the code, just like in the previous flow. We still have a code, and we're going to exchange the code for the access token. But in this case, we need to send the code plus the code verifier. Without the code verifier, there is no access token. So this helps us in situations where there might be someone sniffing the traffic between the user and the authorization server. So if this malicious user grabs the access code, they won't be able to exchange it directly for an access token because they don't have access to the code verifier. So it helps us prevent those situations. And like I said, it's also recommended to use this flow in applications with content that dynamically rendered in the server. Now, not all providers are going to allow you to do that, and it's not the end of the world. The backend is still secure, and it's still a safe place to interact directly with the authorization server, but there is the risk of someone watching the traffic and getting hold of this access code that they will exchange for an access token. So we need to be watchful of that. And some services have different ways of handling these situations, using the concept of the state between the requests that you need to manage in your backend. Next one, client credentials flow. This is a flow designed for machine-to-machine communication. So think of microservices, for example. It would be really annoying to implement the whole flow, the whole pixel flow, for example, for microservices. So instead of doing that, what we do is we exchange a secret directly for an access token. This is the weakest of all the flows. So we need to make sure this only happens in a very restricted environment. And we want to make sure we are rotating those secrets often, because if they get leaked, then someone who gets access to them, they get access to the system, and then we have a huge security hole right there. It's easier for microservices, but we need to make sure we control the conditions in which this exchange of secret happens. And also we need to rotate, always rotate your keys, rotate your passwords, rotate your secrets and everything. And the final flow is the refresh token flow. Every token has an expiry date to keep it secure. And when the token expires, we need to obtain a new token. But instead of going through the whole flow again, we use a refresh token flow to obtain a new access token. In this case, we will also obtain a new refresh token, because the refresh token is only one-time use. And again, when the access token expires, we will use it again. JSON web tokens, or JWTs, or JWTs. I've been talking a lot about tokens to authorize requests to our servers, and there are different protocols and different formats for these tokens. The most commonly used one is JSON web tokens. A JSON web token is essentially a JSON payload that contains claims about our user and about the rights they have to access our API. There are different ways of classifying JSON web tokens. One common classification is between ID tokens and access tokens. So we're going to see later in the context of OpenID Connect, when a user successfully logs in with the provider, they're going to get an ID token and an access token. The ID token contains identifying information about the user. It doesn't contain anything about access rights to anything. And ideally, that token doesn't fly between services and requests. It's only one time sending from the provider to the user, stays in the client. We used it maybe to populate user details in the UI, and it stays there. What we use to authorize access to an API is the access token. And the access token shouldn't contain any identifying information about the user. So let's see what a JSON web token looks like. It has three parts. The first one is the header, which contains metadata about the token. It identifies the token as a JSON web token. It also tells us which algorithm was used to sign the token. In the context of JWTs, the two most commonly used algorithms are HMAC and RS-256. The preference is to use RS-256 because by default, they are secure, because we are using a private key and a public key. If the public key gets leaked, there is no problem. We can only use it to validate signatures. What we need to make sure is that the private key never leaves the authorization server. It's only needed there. We only need it in that server to issue the tokens, and that's where it stays. But we rotate it just in case someone gets hold of the key, because then they can use the key to issue new tokens. So we rotate the keys as often as we can. And if we use the HMAC, it uses a secret. And so in this case, we need to reproduce the signature. So it might be a little bit slow if the signature is very large, corresponds with a large payload, and has a long password. This signing algorithm may be secure if we use it correctly with very long and random passwords, and if we rotate it frequently. This algorithm property here is the one that a malicious user may want to try to set it to none, so that we bypass the signing validation of the token. So what we need to do here is make sure that we have an expectation of what is the signing algorithm when we validate the token. Because we have control, even if we are using a third-party provider like Auth0 to issue the tokens, we can configure the algorithm that is used to sign tokens. And so we have that expectation in our code. If we find something else, we reject the token straight away. Then the next thing we have is the payload. Those are the claims about the user and the right they have to access our API. It contains data such as the server that issued the token, the subject, and that is the user. So that could be something like this. It looks like an ID, but it should be an opaque ID, something that doesn't have meaning outside of the authorization server. And this could be some sort of hashing or encryption on top of the actual user ID. It shouldn't be something that a malicious user can see and try to use to launch a surface attack on our API. It should be something that is not an API resource, okay? Something that is opaque, only makes sense to the authorization server, but it's consistent. And it's something we can use in our API to link users and resources. And so to enforce those user-based access controls. It also contains the audience, and this is a very important property. The audience has to be our API. If it's not our API, we'll reject the token straight away. It has the information about when the token was issued at time, and also the expiry date. The expiry date is also very important. We want to make sure the token hasn't expired before we allow users to access the API. And the final part is the signature. The signature proves that the token is legit, and it's the first thing we should validate. If the signature doesn't work, then we reject the token straight away. So that's a JSON Web Token. And about validation, that's the idea, right? We validate as many properties as we can. We know what should be the value of many of these properties, and we have those expectations in our validation process. OpenID Connect, what is it? OpenID Connect is an identity verification protocol. So if a user has an account with Google Mail, Facebook, or something like that, they may use their account or their identity in those services and bring it to our service. What they're doing is just managing the identity of the user, make sure that they are who they say they are. And so OpenID Connect is built on top of OAuth. It uses also the concept of a flow to prove the identity of the user. And something like Auth0 would take care of all these integrations with Facebook, Google Mail, Windows, and so on. And it will take care of making sure the integration is correct, the user proves the identity, and then issuing a token that is valid for our own APIs. You can use OpenID Connect also with Azure. So they have Active Directory, and in Active Directory, they have the concept of a custom web API. You can use this to register your services with Active Directory, and you can configure that to issue access tokens specific to your web API. So there are a lot of choices in this area. So that's how it works. A user, they connect to the OpenID Connect server. If login is successful, they get an ID token, which, like I said before, is a token that contains identifying information about the user, and they contain the access token. The ID token remains in the client, doesn't leave that application, doesn't go back and forth, but the access token does. That's what we use to validate user access to our APIs. All right, so next one. We're almost finishing here. Vulnerable API designs. Otherwise put, how can our design compromise the security of our APIs? There are different ways. These are just some ideas, heuristics that you can use when you are designing your APIs, so to make sure they are designed in a resilient and robust way to prevent ways of hijacking your services. So there are different ways you can expose vulnerabilities. If you have arrays in a schema and those arrays are unbound, and therefore you're not validating for a maximum number of items, a user can leverage this to include millions of items and overwhelm your server when it's marshalling these payloads and transforming it into objects. Memory consumption can be very high there, CPU consumption as well, and it can overwhelm your servers. Leaking objects. When a user sends a request to the API to list or collection endpoint, and we return all the items, including those that the user shouldn't have access to, and we expect the client to filter out items that the user shouldn't see. So we are delegating this to the UI. The problem is a user looking directly at the traffic will see all these objects and may use them to launch a surface attack on the API or try to get hold of resources that they shouldn't be able to access. Free-form strings. I mentioned this before. If we have strings as part of any input, a user can try and include a SQL injection attack. So if we can enforce or if we can constrain values here via enumerations or regular expressions or something similar, all the better. If we can't, well, let's treat these values always carefully. Integer IDs. Sometimes it's inevitable. We have integer-based primary keys in our database, but what happens is it creates a predictable way sometimes of looking for resources in our API if those IDs are directly exposed to the user. So if we can, avoid integer IDs in your API. Exposing server-side properties in user input. This is related to the mass assignment vulnerability that I explained before. So if a user is not allowed to overwrite a certain property, we don't expose it through the design. Flexible schemas with unknown properties in OpenAPI and JSON schema by extension. So JSON schema allows any property by default. We need to use properties called additional properties or unevaluated properties if we want to ban the presence of non-declared properties in the schema. So whenever we can, please let's use this, because otherwise just the way this validation process works, a user can include a ton of additional properties. It opens the door for mass assignment and also for attacks to try and send very large payloads and collapse our server. Too many IDs. This is related to the vulnerability we mentioned before when we are exposing too much data to the user. So we want to make sure we only expose the data that the user needs, not too many IDs. Improper pagination may allow a user to play around with parameters and make us load millions of items from the database and send them through the API. This may put a lot of pressure on our servers. Unrestricted filters. Again, in our listing endpoint, we may allow users to filter items by certain criteria. They may be able to use this to include a SQL injection attack. And finally, very flexible schemas with optional parameters. These may make validation very difficult in the backend, and it may open the door for data corruption in the backend, or also for payloads which are difficult to process in memory. So that's about design. Next one is vulnerabilities around the API. So these are components around the API. Like I said, an API is not a standalone component. It's actually an interfacing layer. It is part of a service. It has typically a database sitting behind. There are cache stores sitting behind the API. There's an infrastructure that runs the API. There is network configuration. So we need to protect all of these elements. So protect the database, put it in a private network if possible, and access the database over a NAT gateway or a Bastion server, if that's possible. Restrict outbound traffic. This is very important to be protected against server-side request forgery. So if a user is including one of those malicious URLs, we may be able to block that outbound traffic by enabling some of these policies. Collect detailed logs and actively monitor them. It's the only way to spot unusual and malicious behavior from our users against the API. And it's the only way to respond on time and take action before it causes any further harm. Use a web application firewall if you can. It can go a long way to capture and prevent SQL injection attacks, cross-site request attacks. So if you can, use one of those. Rate limit requests, like I said, do it per IP, per account, perhaps per endpoint. So sensitive endpoints and expensive endpoints, make sure they have stricter rate limiting policies. And restrict resource consumption as well. So don't let your services scale to the infinite because you will go bankrupt. But as well, if you can, constrain the amount of CPU and memory that every container, every process, every thread, every request can use to serve the request. And finally, use safe packages and libraries. So of course, we're going to use dependencies. It's inevitable, but there are a lot of ways these days to continuously analyze the security of those packages. So let's make sure that we have always up-to-date and secure packages in our development workflow. And finally, automating API security testing. So ideally, to deliver safer APIs, we want to shift left our security checks. A lot of the time, security testing is done once the API is deployed, so in dev, staging, or production, and any testing is better than none. But if we can, the better strategy is to shift left and to run those tests as early as possible. So we can use tooling to do those tests in an automated way. And as it happens, most of the API security testing tooling is proprietary and vendor specific. There is not a lot of options in the open source space. So to bridge this gap, I've created Fencer. Fencer is still a work in progress, but the idea is it will cover all the vulnerabilities that I covered in this presentation and more, and give you a good baseline of the security position of your API. That said, automated security testing doesn't exclude your own job of assessing your security, because not everything can be automated. We need to look at API security holistically. Like I said before, we need to look at those components around the API, and some of those assessments cannot be automated. And also, you have knowledge of the API. And to be honest, the best security tests are written when you know how the backend is implemented. You know your database, you know your programming language, you know your business model, so you can write better tests, better suited for your API requirements. Perhaps we can do a webinar another day to learn about how we write those tests. And again, you can automate them. Once you write them, run them continuously in your continuous integration server, and make sure that your APIs are always secure. Again, shift left this testing process. So that's all I wanted to say. Thank you for listening. These are my contact details. I hope you enjoyed the stream, and I hope to see you soon in another edition of this event. Thank you.